Good morning, folks. Gary Ducharme here. I wanted to talk to you this morning about the refrigeration cycle and the importance of understanding what the refrigeration cycle is and what it tells us about an operating refrigeration system, whether it be a comfort air conditioner or a walk-in cooler, a walk-in freezer. We're just going to be changing refrigerants, changing equipment size, but the basics are the same. They never change. What we're seeing here is what we call a pressure temperature chart, PT chart for short. Now, if you're working in the field, you're going to be using information that you can gather from this PT chart as you're servicing and troubleshooting or installing any kind of a refrigeration system. Also, the PT chart is the only information that you are allowed to have on you in your person when you take the final exam for the 608 certification. And I wanted to point out, and I will constantly here, that there's a lot of information on this PT chart that not only helps you with a couple of the calculations that you're going to be doing on the exam, but also many other questions can be answered by looking at this PT chart. Some of these things that you may think you're going to have to memorize, you do not. You're going to have a lot of information on this PT chart. For example, questions about low pressure refrigerants are right here. The answers are in this PT chart right here. Medium pressure refrigerants. You may be asked if R134A, for example, here is a medium or low temperature refrigerant. Your answer is right here. It is located with the medium pressure refrigerants. The same can be said for high pressure refrigerants. For example, R410A, which we use today in comfort cooling. That it replaced R22 in manufacturing for comfort cooling. R410A is a high pressure refrigerant. And a very high pressure refrigerant, there is going to be a question, I would assume, on every test about what a high pressure refrigerant might be. What would be the name of a high pressure refrigerant? And here you can see it's R744, carbon dioxide. It's the only very high pressure refrigerant. Also, information about the GWP, which is the global warming potential of any of these refrigerants, what it's rated at is available for you. The class of refrigerant, for example, R22 here is a high pressure refrigerant. It has a GWP of 1810, and it is an A1 refrigerant. Now, an A1 refrigerant, we're going to learn through going through the course, is non-flammable. Okay. 410A is a high pressure refrigerant. Its GWP is higher than R22 at 2090. Now, that was not taken into consideration when this was created, this R410A. What we were trying to do when R410A came into the world is we were trying to save the ozone layer. Okay, R22 has chlorine. R22 is an ozone depleting refrigerant. R410A is not. It has a slightly higher global warming potential, and that's why we're phasing it out now. And we're changing to refrigerants that have a lower global warming potential. Some of those refrigerants will be mildly flammable, for example. And the A2L refrigerants are mildly flammable. And these are some of the A2Ls that are used in commercial refrigeration right now, in window air conditioners, in walk-in coolers, reach-in coolers and freezers now. So there's a lot of information on these 2 pages. You're going to be able to have these 2 pages with you when you take the exam. So take advantage of all the different points of information that you can use to take your exam. So what we're looking at here with the pressure temperature chart is refrigerant at saturation. So by saturation, we mean that refrigerant that exists as a liquid and a vapor together. That is the saturated state of refrigeration. If we're talking about saturation, we're talking about liquid and vapor existing together. So, for example, this PT chart is what we use in our manifold set. Now, here's a circular PT chart, basically. But this PT chart is something that we use for testing. And if we're testing with our pressure, which is on the outside curve of here, going around, that is our pounds per square inch gauge. This is a refrigerant gauge. This refrigerant gauge on the inside is our temperature. Okay, so this is a PT chart in circular form. If you have a relationship here with a pressure and temperature, you have saturation. You can also tell if your refrigerant is subcooled by looking at this, either the PT chart or the circular manifold gauge here. We're going to talk about when refrigerant is not in the saturated state. Refrigerant changes state as we work with it. So I've done a drawing here that I want to go through with you. This is the refrigeration cycle from start to finish. Now, I have drawn the compressor here. Typically, the compressor is located inside of the condenser here. I brought it out here just so we could see what's going on inside of the compressor and separate it. But typically, this compressor is inside of the outdoor unit. And this evaporator that we see here is typically always inside of the air handler in the house or a furnace in the house. It's always going to be indoors. Your condenser is always going to be outdoors. So assume that this evaporator here is sitting in a fan coil or a furnace in your basement or your attic. And we're just talking about the evaporator here and not the fan coil as much. We do know that the fan coil brings air from the room over across this evaporator and goes out into the room as conditioned air. So just assume that is happening here. Same thing with the condenser. We have outside air that's being drawn in by this fan, coming across the coils and exiting on the top out into the atmosphere, where we really don't care what happens to it. So basically, let's start. We're going to use the PT chart and we're going to use this diagram to go through the vapor compression cycle. Now, this is very, very important to learn. It is part of the 608 examination, and it is on the very beginning of the test. You're going to be asked to understand the vapor compression cycle. So by vapor compression, we mean we're going to compress vapor. The compressor is a vapor pump. It wants to have cold superheated vapor, and we'll talk about what superheat is shortly. And it's going to compress that superheated vapor into a high pressure, high temperature vapor. So the compressor wants vapor, just like you and I are breathing air, which is mostly nitrogen and oxygen. The oxygen and the nitrogen have very, very low boiling temperatures. So the air that we are breathing is superheated vapor. The nitrogen is superheated vapor and the oxygen is superheated vapor. That's what we're breathing. So think about this compressor wants to breathe in superheated vapor. We don't do well with liquid. The compressor doesn't do well with liquid. Liquid refrigerant coming into the compressor here can totally destroy the compressor. And we'll talk about that as we start going around the cycle. So let's start at the compressor. And let's assume that we have a valve here on the compressor. And the valve is similar to, and we have a set of manifolds on this compressor. And we're looking at a manifold gauge here. We've put our gauges on there. And we're looking at R410A, okay, R410A, and we're saying that, okay, for R410A, we want a 40-degree evaporator. So on the red line on R410A at a 40-degree evaporator, we are going to be looking at, let's go back to the PT chart here. this 410A, if we have a 40-degree evaporator, say we're looking at 130 psig. 130 psig on our manifold gauge is what we have. If we look at 410A, we have temperature on the right side, temperature on the left side. That's just there so we don't have to read all the way across to get to our saturated pressures here. This is all pressure, this is temperature, and this is temperature. So let's look at our 410A, and we'll go up to 130 psig. This is all temperature, pressure in psig. So here's 130 psig right here. Oops. Sorry about that. Now, if we look across from 130 psig to the temperature at saturation, meaning at this 130 psig inside our evaporator, we have a mixture of liquid and vapor, then we're looking at 45 degrees saturated refrigerant. So if we look into our evaporator on my chart here, in our evaporator here, we have 45-degree refrigerant. Now, I've drawn it so it's a mixture of different colors, meaning it's at saturation. So this refrigerant in the evaporator on the low side of the system, which is everything between the expansion valve and the compressor, the expansion valve and the compressor divide the low and the high side of all refrigeration systems, whether it's an expansion valve or whether it's an electronic valve or whether it's a fixed orifice, it still divides the low and the high side of the system. So on the low side of the system, we take a pressure reading and we're at 130 psig. Now our evaporator temperature, the saturated refrigerant in that evaporator will be at 45 degrees at 130 psig. So that's what we're looking for. And we have designed our 410A to evaporate at 45 degrees at 130 psig. For example, you see on the top here, we have this water, a pan of water on a stove that's being heated. Now, water boils at 212 degrees at atmospheric pressure. So atmospheric pressure is the pressure that's on every square inch of us from the atmosphere, which would be 14.7 pounds per square inch. So at atmospheric pressure, water, which is a refrigerant, can be used as a refrigerant. We have used it as a refrigerant, boils at 212 degrees. So we have manipulated this water to boil, and the vapor coming off the top of this pan is actually warmer than the water. Okay, the water will stay at 212 degrees because it's at a certain pressure, atmospheric pressure, 14.7 pounds per square inch. So if we add more heat to this pan into the liquid water, what happens? Does the temperature of the water increase with the heat that we add to it? No, it does not. This water will stay at 212 degrees and continue to boil until it's all gone. And then the pan might raise up in temperature, but this water will stay at 212 degrees. Very similar thing is happening inside of the evaporator, whether this is a comfort cooling system or a walk-in cooler or walk-in freezer. This refrigerant is boiling in here, picking up heat. So all the heat that we could add to this pan, say we took a torch and put it on both sides, 2 torches, and we just kept torching heat into this pan, it's going to take that heat and boil, and that heat is going to come off the top of the pan with the vapor. But the temperature of the water that's in the pan is going to stay constant at 212 degrees. The same thing is happening inside of the evaporator. The evaporator is staying at 45 degrees. The heat that's coming from the room can be possibly 90 degrees if it's turned on a hot day, can be 70 degrees. It still has more heat than the 45-degree refrigerant that's saturated, that's boiling inside the center of this evaporator. So because it has more heat, And one of the laws of thermodynamics are that hot goes to cold. This heat and this air coming across the coil from the room, say it's even 75 degrees, that heat is going to be given up to this refrigerant, just like the heat that we would add with a torch to this pan on the stove would be given up to the vapor in the water boiling. This is going to stay a constant 45. That heat is going to start to raise the temperature, just like the steam will take the temperature from the torches that we're aiming at it and increasing the temperature of what we're boiling. It's going to take that heat away into the atmosphere. Well, here we're taking that heat and we're going to boil that refrigerant into vapor at the top of the evaporator. Any evaporator that we're looking at, refrigerant enters the bottom and vapor comes out of the top, hopefully, if we have enough air coming across here. So it's the same principle here as we have boiling our refrigerant. We're coming up into the vapor line that's going back to our vapor pump. Now, it's important that we make sure that we have vapor going back to the pump. So we do that by making a measurement. So we're boiling refrigerant here. The heat is being taken from the room. Now the air that comes off this coil and goes into the room has given up its heat at 75 degrees. Typically, we're talking 15 to 20 degree temperature difference. So we're talking 50 to 55 degrees supply air temperature. Now, the heat that was in the 75 degree air coming into this evaporator has gone into the refrigerant. So the air coming off the top has lost that heat. So that heat going into the refrigerant raises the temperature of the vapor. And that's just what we want to do, okay? This is still 130 psig in pressure, okay? But now, instead of 45 degrees, this vapor line, if we took a thermometer and put it on this copper line coming out of the evaporator, maybe 48 degrees or 49 degrees or 50 degrees. Let's say it's 50 degrees. At that point, we are no longer on the PT chart. We are not at saturation any longer. We are in a vapor state. In a vapor state, there's no room for anything on this PT chart. There are no vapor temperatures and pressures on this chart. This is strictly saturation, which means that we have a combination of liquid and vapor. So we're coming out of the compressor, out of the evaporator, I'm sorry, and we're still at 130 psig. We're still reading 130 psig on our manifold gauge. Now we know, hopefully, coming out of the evaporator here, even though we don't have a temperature reading on it, that we're above 45 degrees because this is vapor coming back. The compressor is a vapor pump. It wants cold vapor. It actually needs cold vapor to keep it cool. That's part of the cooling process of this compressor because it gets very hot during the compression cycle. We'll talk about that in a minute. So we have vapor, very cold vapor coming back here. Say it's 50 there. It starts to pick up heat as it comes along, and it comes into the compressor. Now, in order to assure that we have no liquid coming to this compressor, we have to make sure that this mixture coming down the line, we can't see inside of it. We have to make sure that this mixture has no liquid in it. So if it is above its temperature at that pressure, okay, just like the water boiling is above the temperature of the pressure of 14.7, it's above 212 degrees up here. It's still 212 inside the evaporator or the pan, but it's above its saturated pressure or temperature. So then we know that we have superheated vapor if the temperature of this line is above 45 degrees. Because we know with refrigerant 410A at 130 psig, the saturated temperature of that refrigerant is 45 degrees. It's on our chart. That's the way it was designed to work. So if we take a measurement just before we go into the compressor, and we're measuring a line temperature here of 60 degrees, which is typical. If we subtract that 60-degree temperature from the saturation temperature, then we get an answer of 15 degrees. So what we would say is that this refrigerant is superheated by 15 degrees. Now, different manufacturers will ask for different superheat temperatures. But typically, if you're operating around 10, 12, 15 degrees in superheat, you're protecting your compressor, and you know that you just have vapor coming in because it's above its saturation temperature for that pressure. Okay. Now, this is something it may take a while to really understand. So we're going to keep on going through here. We come into the compressor. The compressor, which again is typically in the condenser, has oil on the bottom of it. That oil is brought up and it lubricates the pistons and everything inside of the compressor, depending, let's say this is a hermetic compressor, hermetically sealed. So this cold vapor coming in is raised in pressure by the compressor, which compresses that refrigerant from a low temperature, low pressure vapor to a very high temperature, high pressure vapor, superheated vapor, because the compressor is a vapor pump. It wants cold vapor coming in, and it will give you high pressure vapor going out. So you have very high, this is the highest temperature point of the system. You may have 180, 200 degrees here. You're not going to be putting your hand on the top of the discharge line coming out of this compressor, which will typically always be inside of the condenser here. So what happens in the first few rings of the coil, of the condensing coil, is we have superheated vapor coming in here. It's above the saturated pressure of 400, the saturated temperature of 418 psig. At 418 psig, now on 410A, and let's take a look back at the PT chart here. If we go to 418 psig, okay, we are at 120 degrees at saturation. Okay, so we're not going to be at saturation at the beginning of this condensing coil. We're going to be at superheated vapor here. So it's going to be above 120 degrees. And that's okay. That's what we want, because we want to be superheated vapor coming out of the compressor. We do not want to have liquid coming out of the compressor. And so at 418 psig, our compressor has taken that low temperature vapor at 130 psig, and it's compressed it up into 418 psig superheated vapor above its saturation temperature of 120 degrees. So this is going to be very hot coming in the first few rungs of the condenser coil as it starts to come down. Just as an evaporator is fed from the bottom and outlet is on the top, the condenser is fed from the top and the outlet is on the bottom. Okay, so we have this superheated vapor coming into this condenser. What our job is with the condenser is to condense it, de-superheat it, and condense it into liquid refrigerant. Okay, this liquid refrigerant we're going to find is where we start at the expansion valve, and that's what we need at the expansion device. I won't even say valve, the expansion device. We need liquid refrigerant there to feed the evaporator properly. So that's the way the refrigerant is designed to work. So we have we have said 200 degrees coming down here, and we start to cool, and this outside air is coming over the condenser. It's being drawn in by this fan and discharge on the top. So that's why if you put your hand on top of a operating condenser, it's going to be very warm. Okay, it's going to be warmer than the ambient temperature outside. Let's say this temperature outside is 90 degrees here. We put 90 degrees here, air coming into the condenser. All right, so we have that law of thermodynamics again, that hot will go to cold. If this air coming across this condenser is cooler than the refrigerant, the heat is going to go into the air and be expelled out to the top. And this refrigerant is going to start to get cooler and cooler and cooler. And that's what happens coming down the condensing coils. This refrigerant is getting cooler until it reaches its saturation temperature for that pressure. So 418 psig, eventually it gets to saturation, which is 120 degrees. Now, it's still, even at 120 degrees, it's warmer than the 90-degree air that's going over it. So it continues to give up its heat at 120 degrees. At 418 psig, this 90-degree air is cooler than 120 degrees. So the heat in this refrigerant is going to go off into this air and be expelled out of the top. As it comes down into the middle and the 3/4 of the condenser here, you can see it starts to change in temperature. And what it is doing here, and I made some different colors here, it's changing, it's starting to condense into liquid. It's still kind of at saturation here, 120, but as it goes further down, it turns into complete liquid. So at this point in the condenser, we are no longer at saturation. We are no longer at 120 degrees. We haven't even exited the condenser yet, but we know that we've given up our heat to this outside air, which is cooler even at 90, even at 100 degrees. There are limits, and I think we're finding that out in areas of the country that have had extreme heat this summer. Some of these units are not designed to work at 115-degree outdoor temperature. So they ran into some problems there. They couldn't get the air cool enough to take the heat out of the refrigerant. Now that heat that's in the refrigerant is the heat that we gathered in the room. Okay, we took out of that 75 or 85-degree air. That heat is now in the condenser and we're rejecting it. We've added to that heat with the compressor by compressing that to get it over the temperature of the outdoor air. That's the job of the compressor, to take in cold vapor and send out hot vapor. Then we cool it down with the outside air, which is cooler than the refrigerant, even at saturation. And as it comes down to the bottom of the condenser here, we start to get into an area where we have solid liquid. There is no longer any vapor in there. We're way off the charts. Okay, this is what we called subcooled liquid. We're beyond the saturation temperature. We're fully beyond the saturation temperature, and every manufacturer of a condensing unit has a sticker on the side of it, and they're gonna say and state exactly what temperature of subcooling that they want. Depending on how much refrigerant is in this system and how much heat is taking out of the room inside, this condenser will be full of refrigerant. The manufacturer says, okay, when you start coming, we're 418 psig everywhere on the high side. We're 130 psig everywhere on the low side. So on the high side here, when we come out of the condenser in the liquid line, we take a temperature reading right here, just as we did going into the compressor. We did it going into the compressor to find out how much superheated vapor we have coming in. We do it exiting the condenser to find out how much subcooled liquid we have leaving the condenser, because that's what we want leaving the condenser. We want subcooled liquid. And the manufacturer tells us just exactly how much subcooling we need, because they know how much refrigerant has to be in this condenser at ambient conditions to make it full and subcool the liquid. So say we come out of here, we're at 120 degrees saturated temperature in the middle of the condenser at 418 psig with R410A. So we come out of here and we take a measurement here and we measure 100 degrees. That's wonderful. That's great. We can say we are 20 degrees subcooled, which means we are absolutely positive that anything in this tube is liquid refrigerant. There's no vapor in this refrigerant because it's cooled down below its saturation point at 418 psig. No vapor can exist if it's at 100 degrees. It's off the charts, right? The only time we look at that chart is when we're at saturation. We're at saturation in two places, the middle of the condenser and the middle of the evaporator. So once we get below saturation in the condenser, now we're turning into solid liquid. We have no more vapor in there. And that's just what we want to see go up the liquid line and head to the expansion device. We're going to be still 418 psig here, but now we're at 100-degree liquid coming out. Now we may pick up a degree or two of liquid because this is going to be exposed to the ambient air, and maybe it's going across a crawl space, or it's outdoors, or wherever it's going. It may pick up a couple of degrees. That's why the manufacturer says, okay, the line set length can be so long. And if it's longer, you've got to add more refrigerant because they want to keep this condenser full and keep that subcooled liquid number up. So this subcooled liquid comes around and it hits the expansion device. Once it does that, what does it do? It drops in pressure. The pressure and temperature relationship go together always. Low pressure, low temperature. High pressure, high temperature. On the condensing compressor here, this is high pressure. It's going to be high temperature. On the low side, once it goes through the restriction device, it's going to be low pressure, low temperature. Now it goes through here and it flashes down. I mean, this will go from 418 psig to 130 psig, just like that. Okay, so what happens is there is a mixture here of liquid and refrigerant and vapor refrigerant. It starts to flash off into headed towards a saturation state. It's still colder than 45. It's going to be coming into about 60% liquid refrigerant and 40% vapor refrigerant as it enters into the bottom of the evaporator. And as it goes up here, it starts to pick up heat immediately, and it gets to right where we want it at 45 degrees, okay? And it starts to pick up heat again from the room. It goes to the top of the evaporator, and now we boiled off that refrigerant. That heat has caused this refrigerant on the top of the evaporator to get out of saturation and go into vapor state, cold vapor, superheated vapor. Superheat means it's above the saturation temperature at that pressure. The pressure and temperature relationship is very important, and we're going to be going over this many, many times through this course. So now we're coming out of the evaporator again, and we're into a vapor, a very cold vapor. It's probably 50 degrees here. As we get down, we've lost a little heat because we have a long run coming down here, even though this line is always insulated, okay, from ambient air, because we want to maintain this cold vapor that's headed back to the compressor, because the compressor needs that cold vapor to survive. It needs it to keep it cool enough to run, because you can see the high pressure coming out of here and the high temperature above 120 degrees at 418 psig is very hot. If we didn't have cold vapor coming into this compressor, it would very quickly overheat and destroy itself. So the whole idea of the refrigeration cycle is it just continues and continues and continues. And we always have enough refrigerant in here, like we always would have enough water if we kept adding water onto this pan so it would never boil out completely. We keep adding refrigerant to this evaporator at this pressure, and the warm air coming across here with enough airflow causes it to boil at 45 degrees. So the whole idea is to keep everything happy here, is to keep everything running smoothly. Some of the things that can happen, say our fan motor slows down, or we have a dirty filter, so we have less air coming into the evaporator. We have a harder time maintaining that 45 degree saturated temperatures. It drops down. Say it drops down, it will. With not enough air or too cold air or problems with the airflow, this refrigerant inside of here can get down to 32 degrees very easily. It won't be at 130 psig. It'll be dropping down. So if we look at our chart again, and we look at 32 degrees, which is where we would be if we started to freeze that evaporator coil. If we had a dirty filter, for example, we are going to start at 130 degrees at 45 degrees, 130 psig at 45 degrees. But if we drop down to 97 psig because we don't have enough load on that evaporator, something has happened, the filter is dirty, or something happened to the fan motor, we can easily drop down to 97 degrees. And that's what we're looking at on our manifold when we hook up. We know we're in trouble then, because at 97 degrees inside of that evaporator, is 30-degree refrigerant. Okay, it's still saturated. There's still liquid and vapor in there, but it's down to 30 degrees. So what happens at that point? The moisture in the air that's coming across that evaporator starts to freeze on this coil. Now, you've probably seen pictures or heard about coils that can just continue freezing and become a big ball of ice. And this is terrible for the compressor, because this means that liquid refrigerant is coming into the compressor, causing damage. As soon as any liquid goes into the compressor, it may not kill it immediately, but over time, it lessens the efficiency of this compressor, and it will take it out eventually. Now, these are all the scenarios. We can talk about a lot of different scenarios, okay? We can talk about the fan motor here cutting out, and this high side becoming too high. So that's all part of the troubleshooting process. But today, I just wanted you to understand this basic refrigeration cycle. And this is a comfort cooling cycle in somebody's home. And this is what's happening inside of that tubing. On the low side, we have very cold vapor. On the high side, we have very high temperature vapor turning to liquid and dispelling our heat outdoors. We're picking up heat from the house. We're picking up heat from the compressor. We're combining that heat in the condenser and rejecting it outside. And this is a continual process, similar to if you were in a boat on a lake and you had a small hole in the bottom of the boat, you had a big sponge and you're just sponging that water, trying to get to shore and paddle at the same time. This is what this is all about. It's a slow, continual, and the key word here is continual process. So I hope this helps. Like I say, this is just the first of many different videos I'm putting onto the blog here as I work with students that are coming in every week, with students that are going to be taking the 608 exam with me. So thank you for listening to me, and have a wonderful day, and I will be back to you soon.